Okay, good morning. Thank you for joining this lecture. I hope you can hear me well and you can see also my video and you can see slides. So today we will continue with Radiosity. Actually, we started this on a bit on the last lecture. We came from a rendering equation to Radiosity derivation. We use a number of simplifying assumptions on the way. Including that we need to discretize the space of computation, so we perform meshing of the scene. We assume that reflectance is defined by just Lambertian surface, so we could eliminate this general bidirectional reflectance distribution function. We assume, moreover, that radiosity over a mesh element is finite, is constant. So what we are going to do today is, once we have this formulation, and this formulation, I remind, was equivalent to the linear set of equation, we'll discuss various techniques actually to solve it. So we will discuss various radiosity formulations that would enable to solve radiosity problem efficiently. I will stop by for some time on form factor computation, and we will go over various techniques that would, in a more or less precise way, compute form factors. I will discuss also meshing techniques, because as you realize, this discretization of the domain has huge impact on the final effect of rendering. Finally, I would like to generalize the formulation that I presented so far, which was based on this constant radiosity assumption over element, and we will try to leave this limitation. And this is why we will move more into direction full-fledged finite element radiosity formulation, where essentially we can assume that radiosity over mesh element is represented by a set of basis functions. This would increase complexity of formulation, but of course would give more freedom in representing radiosity over mesh elements. And finally, I will discuss practical techniques that will be relevant also in the context of Monte Carlo computation, in particular in the context of photon mapping that we'll discuss at a certain point. Because rendering techniques, actually how we render image, will be very similar in the case of radiosity and photon mapping. We'll use so-called final gathering technique. So if you would like to look into some textbooks on radiosity, there were a number of those. They are relatively old. But nevertheless, I base material of this lecture pretty much on those materials. So if you would like to read a little bit more, please feel free to look into those textbooks. So this is more or less when we finished last time. We came from a rendering equation parameterized, as you can see, over surface elements. Another formulation that we discussed last time was formulation when we perform integration over solid angles. This equation is used this second formulation that I introduced over surface areas. And then we derive this set of linear equations based on the number of simplifying assumptions that I just mentioned. And we said also that important factor in all those computations is so-called form factor, and form factor groups all kind of geometric considerations in the scene. So essentially in this set of linear equations, you see that this radiosity, which is unknown, is decoupled from geometry of the scene. So whole geometrical information is hidden in this form factor. So whole geometry of the scene, including meshing mechanics and so on, is encapsulated in form factor. I mentioned on the last lecture some basic properties of form factor. Yes, so essentially we have two mesh elements, and I compute form factors from element I with respect to element J. I essentially would like to know what fraction of energy distributed by patch I will arrive to patch J. So this order of indexing is very important. So I am saying about energy distribution from patch I towards patch J. And this is a fraction. This is dimensionless quantity. We mentioned also that we have this reciprocity law. So once you know form factor between surface I with respect to surface J, you can derive form factors from surface J towards surface I just by using this equation. All form factors sum up to 1, and form factors for flat surfaces, for flat mesh elements, is equal 0. Of course, if the surface is concave, as maybe as shown in this slide, this form factor between surface itself may be not 0. So you may have some distribution, some exchange of energy within patch element. And nevertheless, typically we assume that our mesh elements are flat, and this form factor between surface itself is equal 0. And then we have this set of linear equations described more in details. So in particular, what happened is that this unknown radiosity, which in this equation is on both sides of equation, is now combined into this vector, and all geometry is placed in this large matrix. So this matrix has this property that I mentioned last time. If we assume that form factors between surface itself for flat mesh elements are 0, then on that diagonal we have values 1. And this matrix is called diagonally dominant because if we sum up all those elements in the row, we may expect that the value will be below 1, yes, because form factors would sum up to 1 for closed environments. If environment is open, some energy will be escaping, like for example, Cornell box doesn't have one wall, and then sum of form factors will be less than 1 because energy will be escaping from this Cornell box. But for closed environments, they will sum up to 1, as I mentioned, but they are still multiplied by reflectance, yes? And because of that, this sum will be less than 1. So this means that matrix is diagonally dominant. And as we will show a little bit later, it will be very easy to solve. I would like to pinpoint your attention. Yes, I stress today that these form factors describes the fraction of energy that leaves surface I with respect to surface J. Yes? So in this first equation that you see here, this is exactly what these form factors stand for. Yes, but on the other hand, you may be surprised. Yes, because we multiplied by Bj. Yes, so radiosity of patch J, you would expect that by interpreting this equation, that the radiosity of patch I is equal to radiosity emitted by this patch plus a radiosity that comes from other patches and is reflected by patch I. Yes? So here we have this reflectance. So the question is why here we don't have form factors Ji, why we have form factor Ij. So there is nothing wrong in this equation. This equation is properly derived. And we can use some simple transformation in order to show exactly form factor direction according to our intuition. Yes. So if we can multiply both sides of this first equation by surface of patch I. Yes. So we can multiply both sides of this equation. And then instead of talking of radiosity, we talk about total flux. We talk about power, yes, because radiosity is outgoing total flux normalized by surface area. So if we multiply by surface area, this left side of this equation stands for total flux. And now you can see that we have this reciprocity rule, yes? And reciprocity rule that I introduced on the previous slides relates form factors between surface ij and form factors between surface ji. So using this reciprocity rule, I can plug it into this second equation, and then I come with the final equation, yes? And what happens here is that this formulation is already intuitive, yes, because on the right side, under this summation, we see form factors from surface J to surface I, and we multiply it by radiosity of surface J. Yes? So this is what you would expect. Yes? So this is intuitive formulation, but the first equation is just shorter. Yes, but it is they are both equivalent. Yes, that was just expressing the first equation more in terms of radiosity, and the last equation was expressed more in terms of total flux. Radiosity was multiplied by surface area. So essentially now this intuition should be clear, yes, because some of them could ask why in the first equation I consider radiosity under the summation, why I consider radiosity of patch J, but why I consider at the same time form factor from surface I in the direction of surface J. And now we clearly see that we can have this last equation, which is more intuitive. On the other hand, it's more complex to compute. This is why we will come back to the original formulation. So now how we can perform other radiosity computation in practice. So we need light sources, we need some input geometry. Then this input geometry should be meshed if we have some continuous surfaces. It should be subdivided into mesh elements. Then we compute form factors between or pairs of mesh elements in a naive formulation. Later, I will introduce more advanced formulation. We need to know reflectance properties, and then we can plug all those pre-computed values in the set of linear of equation and just solve it. This leads to radiosity solution. But please notice that we solve radiosity kind of per mesh element. Yes, so for each mesh element, we have constant radiosity value that was found as a result of this solution. So how we can render image? So we need to define camera, we need to specify viewing conditions, and then employ some rendering equation, Z buffer, for example. Yes, Z buffer would be very good in showing meshed surface, and we can perform some form of lighting interpolation. Another way would be just ray trace this scene. Yes, so we have many options. So what is important is that radiosity solution is view independent, which means that this is in some sense an advantage, yes, because then we can do walkthrough, we can record some flying camera, we can render images for many regions that are interest. We can zoom in to some regions and so on and so on. Yes, and we can run also interactive navigation in such pre-computed radiosity environment. And this is why I will come back to this a little bit later. We mentioned radiosity because in the context of gaming, very often radiosity problem is solved and pre-baked into mesh elements, and then we enjoy during game kind of global illumination, and we don't spend much cycles on its computation because everything is pre-computed, and everything is pre-computed in view independent way. So essentially we can freely change camera position, and we can refer to visible portion of the scene, and radiosity solution is there. So here is what happens. Yes, like if you would like to get relatively good precision, we would split the scene into small mesh elements, and then we compute form factors between each pair of elements. And also we introduce information about light sources and reflectance, and then we are ready with solution. What is the outcome of the solution? So on the left side of the slide, you see precisely the outcome of this Radiosity solution. You have fixed mesh elements, and you have constant value per mesh element, and that's it. So if you would display image directly applying constant radiosity value to each mesh element, you will see discontinuities, as you can see it on the left side. Yeah, so that's not desirable. So what we are going to do, we will perform linear interpolation. So we will bring the value of radiosity. So for example, when you consider a given vertex, we will take neighboring 4 mesh elements, and then we will average, maybe weighted by the area of mesh elements. In this case, all mesh have the same area, but this doesn't have to be the case. We can weight by the surface area of mesh elements and calculated weighted average of radiosity at this vertex. And then we can apply linear interpolation. This would be equivalent to Gouraud shading. What we'll get here is the outcome of such linear interpolation. So still it looks like our mesh elements were too large, and I will come back to this problem a little bit later when we will be discussing adaptive mesh subdivision. So you see some artifacts, yes, like shadows are blurry. Of course, when we have area light source, you should expect a little bit blurry shadows, but this blurriness comes from meshing, yes. So what also you can see a little bit like patterns, they will be called Mach patterns, because while we linearly interpolate radiosity value itself, we don't we don't provide any mechanism to get a continuous first derivative of radiosity. So essentially, we have piecewise constant interpolation. Radiosity value across boundaries change smoothly, but derivative is discontinuous. And this may cause such visible artifacts. So you can see that on the wall, everything looks fine, but on the floor, when we have more complex lighting distribution, such undesirable effects may be visible. So what I do now is I just use Z-buffer and I directly render radiosity solution. So this would be very, very fast. This can be used in games very efficiently. I will show later some more advanced techniques when even on a relatively imprecise radiosity solution, through this final gathering procedure, we can get really top quality images. So let us spend a few minutes on a form factor discussion. So we have 3 kind of obvious formulations. So one is differential formulation between infinite small surface elements. And these form factors, so we get rid of integral because we assume that those elements are infinitely small, so the distance is constant between them. Yes, so they are small enough, so we can just assume that this R is representative. Yes. On the other hand, if we would consider distance between this corner of this patch and other corner of another patch, when those patches are close, R will be different. Yes, so distance will be different. So for these infinitely small patches, we can assume the distance is constant. The same we can assume concerning those orientation angles of those patches with respect to this line connecting them. And we assume visibility from small patches. Probably this will be also binary, visible or not visible. Then we can, when our task, so when we have infinitely small elements, this equation would be good enough. And in practice, very often we'll use it also for larger elements under assumption that they are far enough. Yes, for close nearby patches, this would be a very imprecise solution. And I should return to my very first lecture. So you see here that we use definition of solid angle. This was an effective surface area divided by squared distance. Yeah? So this solid angle definition is there. And I mentioned that the solid angle definition is an approximation which is valid only for large distances R. I mentioned that the size in one dimension of this surface element, AJ, should be 5 times smaller than distance r, then this approximation is below 2%. You see clearly that this approximation is carried also to form factors, because here also we have some notion of solid angle that we compute. And here we have differential finite formulation. So we compute form factors between differential element the dAi with respect to the whole mesh surface AJ. So this time we need to perform integration over surface AJ, which means that, as I mentioned, when distance between surfaces is close, then we cannot assume that r is constant, r would change. The same would happen also with those angles. This is why we need to solve this integral. And finally, if you would like to have a finite formulation, so really what is important for radiosity computation, compute form factors between complete mesh elements, we would need to perform integration over both such elements. And then here additionally you see this normalization by the surface AI. So we come back to complete definition of form factor. This is what we will use very often in practice in computation, or where we formulate Monte Carlo kind of formulation of form factor computation. So we will perform integration by means of Monte Carlo techniques. I'm going a little bit upfront with respect to the lectures that would come. Then you will use this simple differential formulation, and you will perform computation. So what are properties of form factors in terms of algebra? So what would be form factor between surface I and the sum of surfaces J and K? We are saying that form factor is a fraction of energy that leaves patch I and arrives to patch K, and then maybe arrives to patch K and patch J. So from this definition, it becomes kind of clear that it's enough to add those partial form factors. This is very nice, yes, because this means that we can split our domain of patches into some small patches. We can pre-compute or compute these partial form factors, and then we can just sum them up. But this was the case when we considered form factor between patch I and patches J and K. When our task is other way around, we would like to compute a form factor between sum of surfaces J plus K and surface I. We need to compute weighted average of those factors, yes, form factor. So one surface can be significantly bigger, and then of course these form factors coming from this larger surface would dominate in this weighted average. So this is kind of important to realize, and when you look into form factor definition, it will be clear why we can sum them up. This comes from definition exploring additivity property, and when we need to compute weighted average. So how we can employ additivity property in application? Yeah, so we can discretize this integral and replace it by summation. And then you see here we compute these differential form factors between tiny small elements. Yeah? So we split this patch into small elements, and we compute these partial form factors between each of those such elements. And then we can just sum them up. So this becomes very simple. Please notice that angles of orientation of patches and distances may change, yes? And as I mentioned when I discussed previous slide, this would be the case when those patches will be very close to each other. When they will be very far, then those differences will be negligible. So here is kind of classification of form factor solutions. Form factors are also important in sound propagation and maybe also in particular in heat propagation. So this is not only domain of radiosity. Essentially, form factor you may think as some geometric factors that describe some properties of the scene. And how we can solve this problem? Yes, so in old days, like analytic solutions have been proposed, yes, and in the textbook, in particular for heat transfer, you will have maybe 100 pages for engineers in old days of form factors between different configuration of different geometries in space, pre-computed and analytically solved. So this a little bit is maybe history. Today we do this numerically. And then we compute area to area, so complete form factors, or differential area to area, so something that I mentioned on previous slide, infinitely small mesh element and another patch. And for this purpose, we can employ hemispherical sampling. We can do also kind of Monte Carlo computation. I will show, just out of curiosity a little bit, these analytic formulations. So the first analytic formulations between differential element and polygon was found by Lambert, so famous mathematician. So Lambertius surface name comes from his name. So he built some theory in very old days. Here I introduce form factors between point to disk, so as it is depicted on the right. So we have some simple configuration that this patch is just under this circle, and then form factors has such value. We can shift this patch, and then we would need to introduce effective surface area. This is why those cosines appear here, yes, because then those effective surfaces, that those patches which see each other, would be smaller. And why this equation is important? Because if you don't know what to do, yes, when you have very close mesh elements and you don't want to perform complex integration, you would like just compute form factor very quickly, you can apply this equation. Why this equation is nice? Because even when R goes to 0, you will get non-zero form factor. Yes, so maybe if you write Radiosity software, you essentially for very small r's, you may refer to such equation, and this equation would be safe in terms of avoiding division by 0. So this is an example from this heat transfer textbook. We have two rectangles, A and J, and then we have some very, very complex analytic solution of form factor for such geometry configuration. I would like to mention that polygon to polygon, which looks like relatively basic problem, but arbitrary polygon with arbitrary number of vertices. This problem was solved in '93 by Schroeder and Hanrahan and presented as SIGGRAPH paper. So you see this span time, yes, at the end of 18th century, Lambert computed analytical formulation for differential form factor, yes, and now towards the end of 20th century, still there was room to do some theoretical developments for more general polygonal configuration. And that, of course, you can imagine, resulted in relatively complex formula, because otherwise it would be found much, much earlier. So when we apply analytic form factors, yes, what we do about visibility, yes? So two surfaces can see themselves only partially, yes? And then, of course, it would be good that we can take into account those effective surface parts that can see each other, yes? Some parts will be kind of occluded. So how we can compute visibility? So the easiest approach would be just to trace maybe 10 rays and compute their statistics, yes? If 3 of those arrive, 7 got blocked, then we calculate form factor analytically, and we multiply it by 0.3. That comes from our statistic of these rays that we trace, and that's it. This way the problem is solved. Other approach would be hemisphere sampling. And I bring this approach because maybe in exercise we'll have a little bit similar problem to solve, but also this bridges essentially form factor computation and use of GPU. You can use GPU hardware to speed up computation of form factors. So let us start from so-called Nusselt analog. And essentially here the idea is that we want to compute form factor between this differential element and this patch element. And you can achieve it in following way. This is not what we do computationally. This is just to make some intuition. So we take patch P, we project it on the unit sphere surface area. So essentially exactly as we compute differential solid angle. So the surface area of this patch would be differential solid angle, as we learned on the first lecture. And now we can project this this projection of P on the sphere onto the base, towards projection on the base of the circle. Yes, and this projection of the base, what is depicted in this slide, is exactly form factor. Yes, so form factor would be equal if we take this patch P, we project it on the sphere, and then this projection we project further onto the base of this unit circle, and then we can get a value of form factor. So why this analog is important? Because when we will do the composition of or mapping of form factor computation into GPU, we will replace this hemisphere by hemicube because we would like to do rasterization. And this hemicube will have like 5 walls, 1 front wall and 4 side walls, and will perform 4 times rasterization of the whole scene onto this hemicube. And why this is helpful? Yeah? So we pre-compute such hemicube, and for each of such pixels of such mini elements of the hemicube, we pre-compute form factor. Yes, so those equations that you see on the left is partial form factor between this particular mesh element with the position x and y. You see in this equation position x and y. We take into account its surface area, and this is a solution of these partial form factors between differential element placed at the beginning of coordinate system and some pixel, if you wish, on the surface of the hemicube. And now we can employ additivity property that I just introduced on the couple of slides earlier. Yes, if this projection of patch J encompass a number of pixels, then of course we can sum up those partial form factors, and those partial form factors can be pre-computed and stored in the lookup table. Yes, the properties of hemicube will be always the same. Discretization into 5 walls. Each wall has, say, 50 by 50 pixel. For each pixel, I pre-compute those form factors. So at the end, what I need to know, which pixels on the hemicube surface represent patch J. And I can achieve it in a very simple way. This technique is called item buffer. Essentially, I can color conceptually each patch into unique color. And then essentially I can read from Z buffer after performing scene discretization, after scene rasterization, I can read what colors belong to a given pixel. And if this color belongs to this pixel, this means that this pixel represents this particular patch from the scene. And then what I essentially will do, I will collect all such pixels with the same color, and I will sum up corresponding to them partial form factors. And this way I will perform kind of integration. I will sum up, I will get form factor between this differential element and complete patch PJ. I have a question. Could you give me feedback? You can see my mouse when I move it on the screen, or
Yes, we can.
Okay, okay. Of course, we can set up various parameters for hemicube. We can get different number of pixels. Then those lookup tables will be of different size. But essentially, you get an idea, yes, that graphics hardware is very good in rasterization. So performing 5 times rasterization of the scene is relatively fast. And if we have those pre-computed form factors, then it will be also very fast to sum them up corresponding to the coverage on the hemicube of a particular patch J. And this way we will get very quickly form factors. So this slide shows essentially how we set up rasterization of the scene. We need to set up 5 different cameras and perform five times rendering. Of course, if we assume now that we solve hemicube for 1000 patches, yes, so 5-time rasterizations, this may take a little bit of time, but also as you notice for static scene, form factors can be pre-computed in advance, yes, and then we can perform a lighting solution for arbitrarily changing light, maybe almost in real time, because it would boil down to solve some simple linear set of equations. And then finally, I would just like to show very briefly, yes, like half of this lecture is about Monte Carlo integration. Yes, so here we have some integrals to be solved. So we can use Monte Carlo method to solve such integrals. And these slides, because we didn't explain details of this Monte Carlo integration, this is why I will just discuss this slide more on conceptual level. You will randomly sample some positions of both elements, and you can connect them by rays. For each ray, you will use this differential solid angle equation to compute these related form factors. And then towards the end, you will calculate just their mean. Yes, so mean of all those form factors. And when theory of Monte Carlo integration will be more familiar to you, you will understand that this way, very simply, in simple way, you solve this integral. And we don't have much assumptions. Yes, those surfaces don't need to be flat. Yes, it's very easy to choose some points on them and send rays, and then compute those partial form factors and then compute their mean. This would be how we can use Monte Carlo integration to compute form factors. Another kind of interesting trick is that if you encompass the whole scene into sphere and you start sending millions of rays, yes, by connecting again randomly chosen points over the sphere, yes. So then form factors between surface A and J will be equal to the number of rays that intersect both surface A and J with respect to the number of rays that intersect just surface AI, yes? So that's another not very practical, but kind of interesting theoretical concept, yes, that you, in the spirit of this Monte Carlo computation, yes, you shoot random rays and then infer from these some useful information on form factors. Yes, so the number of rays that intersect both patch AI and AJ, normalized by the number of rays that intersect just patch AI, would give you a form factor. Okay, so let us discuss now practical techniques so now we know very precisely how to compute form factor. We can choose our favorite method of choice. And now we would like come to actually solution of this linear set of equations by trying to capitalize on those particular properties of this set of equations. So we have here this matrix formulation that I have shown already on previous slide. And then you can write it in the compact matrix form. And then it becomes kind of clear that unknown is kind of radiosity. This is why you can invert this kind of transfer matrix and combine the radiosity on both sides of the equation. And why we have this radiosity on both sides of equation? This is consequence of this coupling operator in rendering equation. Yes, that radiosity, to compute radiosity of a given patch, we need to know radiosity of all other patches, but those radiosity of all other patches are affected potentially by radiosity of this given patch. Yes, so we are talking here about global illumination. So we would need to solve for radiosity more or less conceptually at the same time. So later we will show also some iterative procedures that can be used for this purpose. So what is the complexity of this matrix formulation problem? Yes, what is the number of equations? The number of equations, essentially the matrix size is n by n, yes, because we compute when n is number of patches. Because we compute form factors between all pairs of elements, yes, so this is the size of this matrix. This matrix is relatively sparse, yes, because for the scene, for example, like the scene with the table, many patches will be occluded, and then form factors between them will be zero. It's less likely that reflectance is zero. Typically, reflectance would be non-zero. So this sparsity would depend on visibility between block elements, between mesh elements. You can decompose radiosity. If you're supposed to solve radiosity problem for the whole building, maybe it doesn't make sense to compute form factors between patches in different rooms, yes, that are clearly not visible. So maybe then you can separate problem, and then still, if you would like to solve it in as a one solution, you will clearly see that you will have some block diagonal structure in the matrix because many elements corresponding to form factors between different rooms will be zero. And then maybe it's more efficient just solve sub-problems for each room separately. So the question is whether matrix is symmetric. So in general, it is not, because form factors are not symmetric, but through reciprocity rule, we can make it more symmetric in the formulation. And finally, a matrix is diagonally dominant. So this I already mentioned, yes, that essentially some values in the rows will be below one, and so we'll have on diagonal ones, and here there will be some small fractions, and this we call matrix is diagonally dominant. So what are properties of such a matrix? One of such properties is called spectral radius, and this indicates the speed, how quickly potentially iterative methods may converge. Intuitively, how quickly we can converge. Yes, if our room is painted with very dark colors that reflect little light, then maybe we need just few iterations and our problem will be solved. But if reflectance is very high, say 0, 90, 95% or something like this, yes, in each iteration, energy that is absorbed, that is attenuated, is very small. And then, of course, we need to consider many bounces. Because of properties of the matrix, we can compute its invert, yes, and then we can apply Neumann series essentially to approximate this inverted matrix. Yes, so essentially, according to Neumann series expansion, this is equivalent to sum of those of this matrix T to power A, when A corresponds to the number of successive terms that constitute this approximation. Also important properties of matrix in radiosity is that problem is well conditioned. So even if we have some small discrepancy, some small noise, some small perturbations, and those perturbations we have, yes, because form factors are not very precisely computed. Everything depends on the cost that, on the time that you want to spend for their computations. So there will be some errors, so there will be some fluctuations. And hopefully there will be no systematic error that we significantly overestimate form factors always, because then we may finish up not converging, yes, because energy would be multiplied. But if you have some more or less random fluctuations, which is typical for some numerical errors in our computations, matrix will be well conditioned and will have self-correcting properties that would allow quick convergence. So formally, what methods we could envision for a radiosity solution? No, pretty much all those methods that we typically use to solve linear set of equations. So formally, we can apply this matrix inversion, but this would be a relatively costly operation, so we don't use it. More popular approach would be related to this Neumann series called Jacobi iteration, when essentially in each iteration, so in the first iteration, we assume that radiosity of light sources is assigned to radiosity values, so nothing special. And then in each iteration, we'll take this radiosity matrix and we'll multiply it by radiosity values corresponding to the current iteration in order to compute the next iteration radiosity. So typical iterative process. And this iterative process is also very intuitive, yes, because this means that here we consider just primary lighting. Here we consider one bounce of indirect lighting, yes, because we use only this first term. Here we use already maybe here is just radiosity that is emitted, and then we multiply it by this matrix, and then we will consider first bounce of light reflection. And then when we add the subsequent terms, then of course we add more and more bounces. So typically, solution converges relatively quickly. This depends on the overall reflectance. If reflectance is 95%, we need many iterations. But in standard situation, when reflectance is around 30–40%, maybe after a couple of iterations, we are good. And as I mentioned, the problem is well conditioned. So solution is numerically relatively stable. So even if we have some small inaccuracies. So Jacobi iteration, yes, if you look into textbooks describing numerical methods for solving linear set of equation, this method will be well pronounced there. And the idea is essentially that we have some iterative process, yes, and in each iteration we update a radiosity value. And please notice that in this formulation, we have like two loops. So first loop is I have some radiosity values for iteration k, and then I calculate radiosity value for iteration k+1, and I solve it completely. And then I assign radiosity values from iteration k+1 to this estimate to radiosity values so that I can prepare for the next iterations. Yes, so essentially that's very clean solution because as I mentioned, each iteration would mean one additional bounce of light. Yes, so this quite cleanly allows to imagine how many times you did 5 iterations. So you allowed that light bounce 5 times. And this is assured in this process. But it doesn't mean that this process is efficient. This is why we have also Guy-Seidel iteration, also called gathering iteration. And it allows for faster convergence. So what is the trick? So you notice that you proceed one by one, yes? You take, you estimate now, you gather, this is why it's also called a gathering iteration, yes? You compute radiosity value in iteration k+1 for a given patch. And then once you compute that radiosity value for this patch, you immediately use it to compute radiosity values of other patches, yes? So here is where we have this speed up. So here we have been in this very clean conceptually solution. We use radiosity value always for iteration k in order to compute radiosity values for iteration k+1, yes? Here, once we solve for some patches, yes, for radiosity value in iteration k+1, we immediately use it. So in this equation, you see this split. For those radiosity patches that we already performed this iteration k+1, we use them immediately. For those patches that, of course, we have not done it yet, we use radiosity values from previous iteration. So this way, we get a little bit of boosting. Solution is faster. But on the other hand, the price that we pay is that we don't have this clear notion how many bounces of light actually happened. Yes, because in this iteration potentially we have more bounces. Yes, like for some patches, smaller number of bounces was considered, and for other larger number of bounces. Yes, and I come back to this notion Gauss-Seidel iteration, also called gathering, because for given patch I, in our formulation, we gather radiosity values from all patches in the scene. So this corresponds if you look into matrix formulation, to solving essentially for one row of such equation. Yes, we gather radiosity value for patch I by summing up contributions from all other patches in the scene. So in order to compute, update all radiosity values, you need to know, of course, full matrix. So this is this gathering step. Theoretical complexity is quadratic with respect to the number of mesh elements, and in order, this is what I mentioned just before, that in order to update all radiosity for all patches, you need to store all form factors. So how this Jacobi iteration proceeds, you have zero iteration, so direct lighting is assigned, you have first bounce, you have some direct illumination, essentially ceiling is dark, and then you have second bounce, light from the floor table comes back to the ceiling. You have two iterations of this solution. Then you have third iteration. You see the difference between third, second gets smaller and smaller. So this means that we nicely converge. Another approach, and this is why the previous approach, this Gauss-Seidel, we called gathering iteration. Now we have we can reverse this process, yes, and we will call this iteration shooting. In numerical methods, this method would have the name southward iteration, but that's not primary choice for solving linear set of equations, yes, and you will understand maybe a little bit later why it is not primary choice, but nevertheless, for radiosity problem, because matrix is so well conditioned and diagonally dominant and relatively problem is so easy to solve, this method that in general would be not so universal works quite well in this particular problem. Yes, so we are talking about shooting. Yes, so we take the patch, possibly with the highest power, with the highest total flux to be distributed. Yes, so total flux would depend on radiosity of this patch, but also will depend on the surface. So if you have a patch with relatively large radiosity and large surface, this would be a good candidate to choose it for shooting energy in the current iteration. So essentially, you can imagine that we want to choose those patches that potentially have the biggest impact on the scene illumination. We don't care too much about very tiny patches that are somewhere dark in the shadow. They will contribute little into global illumination. So we will consider them, but we will consider them at later stages. At first, we will focus on considering those patches that contribute the most significantly. And this is, observation is important, yes, because then in the iterative process, relatively quickly, we'll get good approximation of the final image without waiting for the complete solution. Yes. So Southwell iteration in this particular case is kind of nice because it gives relatively quickly approximate solution. If we would like to fully converge to high quality solution, this would be not optimal procedure. This is why it is not so commonly known and used for solving linear set of equations. So we essentially can formulate it into some pseudocode. So initially, we will use two variables to store radiosity. One would be we store actual radiosity per patch, and another variable we use is kind of new term. We'll call it unshot radiosity. Yes. So initially, we initialize them by assigning emitted light from light sources, yes, and the rest of them will be equal just 0. And now we start this loop. So in the first step, we pick up a patch with the largest total flux. Yes, so the patch that has the largest products of unshot radiosity multiplied by surface area. Yes, so this means that yes, in first iteration we'll take just light sources. Yes, because they have largest unshot radiosity, and then when we continue, we'll take non-light sources patches with the highest total flux to be emitted, but exactly in this order. We will be very aggressive in choosing the most important patches in terms of lighting distribution. And then what we compute? So we compute some partial radiosity coming from this unshot radiosity, and we perform computation for patch J, yes? And then we update in the next equation, we update unshot radiosity by adding this value, and we update also total radiosity. Yes? So in this loop, we always keep account of total radiosity accumulated at a given patch, and then we also accumulate unshot radiosity. But important step is what you see when you leave this loop. So in this loop, you shoot radiosity from patch I towards all patches J in the scene. Yes, so exactly as it's shown here, you shoot this radiosity. Yes, and when you are down with shooting radiosity from this one patch, you assign 0 to unshot radiosity for this patch. Yes, so this patch would be not considered for many next iterations as an active shooter of energy, because its energy will be now very slowly accumulating. But at certain point, again, you may reach this state that this patch got enough energy to be considered again. So this is also a not very effective thing about Southwell iteration, that we potentially come back to patches. And although, as you can see, here we need very limited number of form factors, just form factors between patch I and J to go over this loop, when we may need to come back to this loop a couple of times, because unshot radiosity for this patch I in the meantime accumulated to some significant value, and we need to compute it again. And then we need to come back to those form factors. So either you store them or you compute them on the fly. Yes. So computing on the fly is more costly, but this means also that this algorithm can run on relatively small memory footprint. And what we can do, this is the last line in this pseudocode, after considering just a couple of such patches with dominant energy, we could display image, and this image will look quite decent. So solution is progressive. Our quality of image will gradually improve the more patches are considered. And at a given moment of time, as I mentioned, you need essentially a column of form factors. Yes, so to move in this internal loop, that's all information that you need to keep in memory. But of course, as I mentioned, you may come back with this unshot energy to this patch after a few hundreds of iterations, and then you will need to compute again those form factors. So choice is yours. Either you store them or you compute them on the fly. So I would like to discuss something that should give you some a nice intuition, in my view, concerning global illumination in general. So can we somehow boost our radiosity solution in terms of displaying some images that are good approximation of what you may expect in the final image? Yes. So we can give it a try. Yes. So after certain number of iterations, after considering unshot energy for certain number of patches, we can compute some radiosity, that state of radiosity, and we can display image. But this image would be dark in the shadow, yes, like because maybe global illumination didn't reach these shadowed regions, things like that. So the question is whether we can approximate the visual quality of the image towards the final quality of solved radiosity. And we will give a try. Yes? So we will use ambient term. So ambient term is maybe familiar from computer graphics 1. when we exactly want to avoid black shadows, yes, when we perform only direct illumination. Here, the notion of this ambient would be more precise. This ambient actually would change, would react on our computation in the scene. Yes? So how we will compute ambient radiosity? We should maybe compute some representative lighting that was not yet distributed in current iteration. So we need to look in the future. We need to look how much of unshot radiosity still remains to be shot. And based on this, we can estimate this unshot radiosity. So this is weighted average of unshot radiosity in the scene. Yeah? So again, it is weighted by surface area. So this gives us some good statistics, yes, of how much unshot radiosity remains still in the scene. And we can apply it skillfully, yes. Another thing is we would like to emulate bounces of this unshot radiosity, yes, potentially many bounces. This light may reflect many times. So what is mean reflectance in the scene? Essentially the same trick. We can calculate weighted mean of reflectance, yes. And here is, I think, a very important kind of concept and line. This reflectance is a fraction. So I can come into series and essentially try to say what would be reflectance, representative reflectance, after infinite number of bounces. And this series can be computed analytically. So now if you assume that average reflectance in your scene is 90%, yes, let's assume that we have very reflective scene. So 1 minus 0.9 is 0.1, and 1 divided by 0.1 means that we have 10. So this total reflection is 10 times. Yes, and now please notice I compute my ambient light in this last equation on this slide by considering this total reflection multiplied by this unshot radiosity. So this looks like we multiply energy in the scene a lot, yes, because this total reflection is 10 times. But we deal this time with the scene that really reflects light a lot, yes. And I would like to come back to this intuition that I gave you on the previous lecture, that solving rendering equation is about equilibrium state, yes, in terms of photons. So we consider photons that came directly from light sources, but came also to this point at this given moment of time, because they were emitted by maybe the same light source much earlier. They had just much longer paths. They reflected many times before reaching this point. Yeah? So we are talking about equilibrium, which means that we consider photons not that are sent at this given moment of time, but we consider photons that were sent into certain time period, but they needed just longer time through many bounces to arrive to this given point. Yes, this is why we have this multiplier, which at first glance may look unintuitive, because reflectance still you would expect that this is a fraction. Yes, that's a fraction, but we consider many bounces of light reflection, and we can compute the sum of this series, and then of course the impact of this total reflection will be much larger. Of course, if average reflectance in the scene is 50%, yes, then we have 1 minus 50, 0.5, then total reflectance is just 2 times, which means that, yes, this ambient term is less significant. Okay, so let us compare what we learned so far. So we learned this gathering iteration and shooting iteration. Gathering iteration is more or less iterative approach to traditional radiosity. This is what we have on the left. We perform scene meshing, we compute form factors, we solve linear system of equation, and we display results. And this progressive refinement or shooting iteration, first step is of course the same, but then we compute just one row of form factors. Yes, we perform one step of solution. We can maybe boost solution by adding this ambient term, and then we are ready to display some approximate image. And this image will be better and better as we continue our computation. So here are results of Gauss-Seidel iteration. So this matrix approach, this more traditional approach. You see that after many steps, after considering just random patches and solving gathering process for them, we converge relatively slowly. Progressive radiosity, which is very aggressive in choosing those patches that contribute most to the scene illumination, converges is much faster. So now I would like to spend a few minutes on meshing techniques. As I show in this initial slide, when we consider these fuzzy shadows and I show you some artifacts, meshing is very important for the final result. In particular, if you would like to use Z-buffer to directly display radiosity solution. So we may have mesh elements that are not carefully prepared from point of view lighting simulation. So in particular, our mesh elements will have poor aspect ratio. So maybe very elongated, like these wooden tiles of this door. They are very elongated. And then, of course, you can imagine then in terms of using this approximation for solid angle or approximated form factors, you will make huge errors when you consider such mesh elements. So essentially, you would like to improve this aspect ratio. You would like that shape of mesh elements is more regular, as shown here to the right. Also, you don't want in the scene to make abrupt transition between very large mesh element and then starting with tiny mesh elements, because you notice that there is some shadow to be reproduced. Yes, this transition should be smooth. So this change of size of mesh elements should be gradual. Also, what is important, we should avoid so-called T-vertices. Essentially, we should remesh for radiosity computation and get rid of this T-vertex. So what is the problem with T-vertex? So you remember that radiosity value at those vertices is linearly interpolated. So for this mesh element to the left, it is interpolated based on radiosity values at this point and at the center point. And for this big patch on the right, radiosity value will be interpolated between this vertex and this very bottom vertex. Yes, so it is very likely, and typically it would happen, that this linear interpolation between two distant vertices would not match linear interpolation that is done with participation of this T-vertex, of this additional vertex. So we will get some cracks. This would be quite well visible. So lighting function will be just discontinuous along this edge. So we would need to split this mesh element into smaller mesh elements, and then we can avoid this T-vertex, and then we can avoid these cracks, these discontinuities. So another thing is that we may consider some higher order functions, some polynomials to describe radiosity, but then again we need to assume some approach to have smooth transition between mesh boundaries, which is not easy. So we should get, and we get, yes, like C0 continuity along mesh element borders under condition that we don't have T-vertices. Still, the problem is that C1 continuity is not assured, and then you may see some artifacts in the forms of marks. So it's very difficult to predict what meshing we would like to apply. We don't know lighting, so it's a chicken and egg problem. Yes, we don't know a lighting solution, and now we're supposed to design mesh that would nicely approximate potentially lighting distribution. Yes, that's impossible. So typically what happens is that we start with some coarse mesh, and then as we progress with radiosity computation, we adaptively subdivide this mesh so that it approximates lighting function. So here we have some shadow boundary. First approach is called error refinement. It's not so widely used. Essentially, you will try to shift merge vertices to approximate position of this shadow. Yes. This is not so practical. Algorithmically, it's more difficult to tackle. So edge refinement would be something that is commonly used, and then that's relatively brutal techniques. We divide those mesh elements when we find some discontinuity of radiosity over vertices or for neighboring mesh elements. We'll subdivide them into smaller mesh elements, and in next iteration we see what would happen. If needed, we'll subdivide them further. This unfortunately would give you not straight, if you do linear interpolation, this shadow boundary would be jaggy, and the jag size would depend on the subdivision of this mesh element. So if you do it below pixel size, which is not practical, then maybe you can solve it. But we should remember that radiosity is view independent, so it's difficult to predict in advance what is the pixel size. Then we can increase polynomial orders. So instead of using just constant radiosity values, we can use higher orders. And then we can do remeshing. Yes? So we can implicitly introduce mesh boundaries along lighting discontinuity. Again, algorithmically is difficult to tackle, but this potentially would give us the highest quality. So how we perform such adaptive mesh subdivision? Of course, we will consider radiosity values at vertices, and if we have huge gradient, if we have a big change of radiosity between neighboring vertices belonging to the same polygon, we will split this edge into two parts. And then, of course, we would need to propagate those changes of mesh, because we need to avoid T vertices that I just mentioned. So if you split the edge in the middle, yes, here this is not correct what was done. We would immediately need to subdivide these bigger elements into two parts, yes? And so that's a relatively complex process, but meshing software can handle this. Essentially, that's kind of adaptive process. And now the question is whether we consider just radiosity value, or we will introduce a little bit of perception knowledge. I will discuss perceptual approaches later, but let us have a look into it. Yeah? So if we perform mesh subdivision just based on energy, this energy doesn't tell you much about the visibility of artifacts. Yes, this is why we may over subdivide mesh elements, as this happened in this particular case. Yes? On the other hand, we may consider those perceptual considerations when we in those perceptual considerations when we just I will try to sign out from Skype. Yes. If we consider perceptual considerations, we take care what kind of discontinuities in energy can be visible, and this may lead to more sparse subdivision. So we will understand those techniques a little bit better. I would like just announce that it is important to understand what human eye actually would see, because without this understanding, you may very easy like exaggerate with computation. You may require much higher convergence of your algorithm that it is needed. Human eye would not see it. Or as in this case, you may require much deeper mesh subdivision, although human eye would not see it. Yes, essentially in those regions of interest, we see the problem. So meshing is a real problem in radiosity. Yes, like, so for example, let us assume that we have wall and we have some mesh elements that are not split along the wall. So this room is illuminated, another room is dark, and then energy would leak under the wall to another room. And this is what really would happen if you don't prevent this by splitting those mesh elements along the wall. And typically when architects design some interiors, they don't care about our radiosity computation. They come with meshes that are for them convenient. In particular, they may consider the whole floor as a huge plane and would not care about walls. We would need to mesh these very carefully. And then you may see also that when we have like area light source and then we have some occluders, shadow relations are relatively complex. Yes? So we have like full shadow ray, which we call umbra, but we'll have also penumbra, some half shadow rays, which means that partial surface of this area light will be visible and part will be occluded by this polyhedron casting shadow. So what we will, in order to reproduce nicely lighting distribution, we can go very deeply with mesh subdivision, and to get good quality of lighting distribution in this scene, to reconstruct direct lighting. Here you see some spotlights. I needed to subdivide this mesh very deeply. But another approach, which would be used maybe in gaming, would be, okay, why I would care to subdivide mesh so finely here? I will just reproduce radiosity lighting by texture. So this is equivalent to pre-baking light into texture. This would be called light maps. And we have traditional texture that describe reflectance, and we have typically 8-bit, just single channel texture to describe just irradiance, yes? And then you multiply this information, and then you get radiosity. So this would be a very efficient way of storing lighting, and this would be efficient way to avoid too extensive meshing, because more complex distribution of light we can just store as texture. So in the current approach, I assume that I compute radiosity between each pair of patches in the scene, but that's a little bit naive approach. Yes, in this scene, you see that if I consider patch P, for some patches that are nearby, maybe I consider exchange of light for the whole patches. But maybe for some patches that are very far, it does make sense to consider them on this level of granularity. So you can imagine some hierarchical approach when energy transfer between P and S3 would happen on the level of maybe the whole shelf of books or this part of the wall. So this is what happens. You can formulate radiosity in terms of kind of hierarchical approach, and this way you can improve computation. Yes? So just to give you some idea, yes, I need to consider radiosity exchange between those two patches, and then I decide on which level of granularity I need to perform it. I can decide it based on form factor value. I may decide it based on total flux that's supposed to travel between those two patches, and refine solution when patches are closely located, yes, and a lot of energy is distributed, then I can go with refinement. So we can build something like kind of quad tree in the mesh space when we introduce this hierarchy of subdivision, and then lighting energy happens not between those big patches, but between appropriate level in hierarchy. Yes? So you will have some oracle that will tell you how deeply you need to subdivide and on which level you need to exchange this energy. This has one problem though, yes, because if you exchange, as it is shown this light energy on this level, and maybe in some other region you went even deeper, you exchange energy between this small patch and some other big patch, you have radiosity distributed for small patches, yes, and then this radiosity would be incomplete, yes, because for some patches you consider it radiosity exchange very deeply in the hierarchy, and for the same area in the scene, you perform energy exchange on higher level. Yes? So essentially you would need some mechanism to inform those higher level patches about energy distributed them. So you should go from top to down. And also you need reverse process going from bottom patches to bring this energy back to the top level patches. So this procedure is called push-pull procedure. And if you are in the computer graphics field in general, then this push-pull name would appear relatively often. So push-pull would appear always when you have some non-uniform sampling and you perform, for example, reconstruction on the surface from some points that are non-uniformly kind of placed. Yes, then maybe you need exchange information between higher granularity elements and lower granularity elements. And this happens exactly as it is shown here and as I mentioned. Yeah? So first we have like push. We go with energy from top level patches to smaller level of patches. And then we calculate we sum up this energy, yes? And then towards the end, we have at each level of granularity, at the smaller level of granularity, total energy that was collected for this particular region in the sea. And now you have also reverse process. You go from those smaller regions, and then you pull energy towards the higher regions. So here we do kind of, we sum up energy. Here we calculate the mean of energy over those 4 patches to calculate contribution of those patches to this patch on the higher level. And this way we propagate energy back. Okay, so again, kind of milestone in this lecture. Yes, we introduced progressive radiosity and now introduce hierarchical radiosity. So progressive radiosity, it was this shooting iteration, yes, produce quickly approximated image. We introduced this procedure for ambient computation. You can get meaningful images even further. It requires little memory because in principle, you may store just one column of form factors in the matrix formulation in the memory at given moment of time. For complex environments, and in particular those when the reflectance is high, you need many iterations and you need potentially recompute those form factors. And in general, this approach is quadratic in terms of computation complexity. So for large complex scenes, it's less practical. So hierarchical radiosity elevates this complexity a bit, yes, because you don't need to perform energy exchange on the level of each small patch. So it is less sensitive for the scene complexity. On the other hand, it's very difficult to introduce progressive scheme here. We expect that you compute form factors between all those levels in hierarchy. This is called kind of linking process. And this typically is done at some form of pre-processing step. On the other hand, this complexity of this linking process is linear to the number of patches, yes, because very often you skip many patches by considering light exchange just on higher level of patches. So there are some algorithms to get rid of links, because those links, as you can imagine, is also memory consuming, so you don't need to store them. And more progressive schemes have been elaborated, but that's not kind of the main line of development in this algorithm. Also, you may have problems with quality, yes, because when you consider energy exchange at with different mesh granularity, essentially I mentioned that a grading of meshing is very important, yes, so kind of gradual change of mesh size. And then this energy exchange of different levels may cause some shading artifacts. And then typically final gathering is used. I will come to this to the end to render scene computed using this method. So here is kind of summary of algorithms that I discussed. Matrix radiosity, Gauss-Seidel, quadratic in terms of computation, quadratic in terms of memory, all form factors needs to be stored. Progressive radiosity, quadratic in terms of computation, linear in terms of memory storage. And hierarchical radiosity, linear in terms of initial mesh elements, in terms of mesh elements that you consider, but quadratic with respect to initial mesh elements in the scene. So if you get the scene with many plants when every leaf is represented as mesh elements, it's difficult to build hierarchy because hierarchy assumes like subdividing those mesh elements, yes? So you need some step, which I will discuss in the next step, in the next slide, is clustering. So it is important to remember that if you get meshing of the scene as it is, still cost will be quadratic with respect to the input mesh elements. So unless you get very coarse mesh, when you yourself in the train of radiosity computation you split, then your costs will be small, yes, because you have small number of initial mesh elements, and then potentially you may finish up with huge number of subdivided meshes, and then you will get this linear cost. On the other hand, when you get already mesh that is deeply subdivided, you need to cluster back those mesh elements. Yes, so you need to group mesh elements. Like in my door example, yes, this time you need first maybe to split mesh elements to get better grading, to get better aspect ratio of those mesh elements. And then you may group many of mesh elements all together, and then this way you will reduce this m input number of initial patches. So now towards the end, I would like to, at least this lecture, I would like to generalize a little bit radiosity that I discussed so far. So far I assume that radiosity value is constant over mesh element. In general, we would like to get rid of this limitation, and we can assume that radiosity can be represented by finite function basis. Radiosity will be computed as a linear combination over these basis functions. So we would need to compute some coefficient associated with each basis function and then sum up radiosity value. So this equation essentially demonstrates this. So we assume some basis functions, we need to solve for coefficients, and then radiosity can be computed. And please notice that radiosity change as position within mesh elements. So we can potentially get quite complex distribution of lighting within mesh elements. So this is attractive because your intuition would tell, if I can reproduce some complexity of light within mesh elements, I can have larger meshes and larger mesh elements. So then my complexity, even if it's linear, would be reduced. So this is essentially the idea that we would like to replace kind of infinitely dimensional function of radiosity for all points in the scene by some limited number of basis function that span over mesh element and get zero outside this mesh element. So let us start from something what we considered so far. So like a constant piecewise constant mesh element values. So essentially our basis function is this box function that is zero outside mesh elements, and then approximation of this lighting distribution using this piecewise constant function is as follows. Yes, we can introduce linear functions, then you expect that this approximation may be typically better. And the same idea, yes, like this is our basis function, linear basis function, essentially. And then, for given mesh elements, we consider already like this. For given mesh elements, maybe you see that those two linear functions contribute to energy distribution. And then we can go into higher and higher, yes, like by combining, by adding complexity to constant function, yes, linear function, quadratic function, some higher order polynomials, and then we may expect that accuracy of representation will be better. And I would like just towards the end, and I will maybe continue this on the next lecture, I would like to just recall that dot product between two functions is just integral over those two functions. Yes, so, and we will denote dot product between those two functions using this bracket notation. And then in order to compute, reconstruct a given function at given position based on basis function, we need to essentially sum up contribution of each basis function, and we'll have this constant coefficient for given mesh elements that will determine contribution of the basis function. And then this basis function, typically we apply orthogonal basis function, and they have such properties that their integral is equal non-zero only when I is equal j. So non-zero integral we have when we compute this dot product between a function itself. When we compute a dot product between two different basis functions, this dot product value will be equal to 0. So now that's kind of trick that we are going to do. We essentially project this equation. We compute the dot product of both sides of this equation with respect to the basis function ni. And I have right, yes, like left side, I compute dot product of this function fx with my basis function. And this basis function is orthogonal basis function, yes. Then what would happen is that I compute also the right side of this equation. And the right side of this equation would be non-zero only if I do this dot product with the same basis function, yes, based on the properties in the upper equation. So then I calculate those coefficients as follows. Yes, so this is projection of my function onto basis function, normalized by dot product of the basis function. Now, if I introduce further limitation to my basis function, I will call them orthonormal basis function. Then dot product would be equal 1. Yes, so essentially denominator here would be equal 1. So we can this dot product simplify. So this essentially equation tells us that in order to compute coefficient corresponding to a given basis function, I need to project my function that I want to reproduce. So I need to project my radiosity function into this particular basis function, solve this integral, and get this coefficient. So now I guess I will finish. So on the next lecture, I will introduce in more details this finite element radiosity formulation. So do you have some questions at this point? Yes. And please use chat. I displayed this chat window and I look into it time to time. So please also try interrupt me this way, yes, or even if you don't mind to be recorded, just speak up. So what would be your questions for today? Everything is more or less clear. So slides following requests, one of you I already posted on the web page, so you can take your notes directly on the slides that that I present for this lecture. So if there are no questions, I would like thank you, and yes, I hope to see you on the next lecture. So thank you very much, and I end this this call.